continue talking about some probability stuff, transitioning towards statistical concepts. Interesting. If you look at curriculum in a lot of statistics department, there are courses on probability and there are courses on statistics. And somehow it's this interesting separation that happens, yet they're kind of all tied together. And so we're started with probability. We're going to keep going, and then we'll transition sort of into statistical concepts in this lecture. And then Friday, just do some more hypothesis testing. And that gets us set up with the kind of background we need to start doing our own data analysis as we go along. Okay. So many of you, I think, hopefully most of you got an email that I sent out yesterday. Those of you in Edgeland, TV land, watching it in their pajamas at home right now. Coffee in hand, uncombed hair. So check it out. I sent you guys an email, but what ended up happening, somehow the class list that the UW generated took 2 days to make, so finally it's ready today. So I'll send out an email to you guys later. All right, so then everybody will be able to get the notes. Now, I did get a request, by the way, to say, hey, it'd be really helpful if we had the notes before class. It would be awesome. So I'm typing these as I'm going here. So you know, the fact that you'll actually get notes, you should just feel lucky. I'm just kidding. Remember, we started off with really low expectations. But I was informed yesterday after class that no matter how low the expectations, you can go lower. I was a little depressed by that. So, but we'll try to keep going up. All right, but lectures will at least be available after class. And if we're lucky, maybe before. I'll see what I can do. All right, so we're going to talk about random variables today. And the idea is to talk about the random variables, and then I will introduce sort of the most famous, the pantheon, as it were, of random variable sainthood. I don't know if pantheon and sainthood go together, but we're putting it together in class. Okay? So we're going to talk about some of the more common ones, talk about some of their properties. These are the ones that you would see over and over and over again. These are the ones that are always assumed in statistical analysis in some sense. So we'll discuss those. All right, so we talked a little bit yesterday about probability theory, calculating probabilities, and so forth. But oftentimes, what we really want to do is calculate some function, really, out of some sample space, an event space. For instance, we're going to go back again. What do you always do? You throw dice and you toss coins. That's what you do in probability theory, or start talking about it. So we're going to start off with 2 dice. Here's a little example, okay, to talk about random variables. The random variable I want to define is the sum of 2 fair dice, okay? So x, my random variable, is the sum of 2 fair dice. Okay, so I don't care about individual values so much as sort of the overall what I get out of this thing, okay? So for instance, we can map out the probability space of this thing and say something like here, the probability that the sum is 2, well, there's one roll of the dice that gives us that. And it comes with a probability of a 36th, right? There's going to be 36 total combinations. And so 1, 1. So, right, this is your, isn't that a bad roll? Like snake eyes, they always make. See, I think yesterday I was totally disillusioned because there's, I always hear about lucky sevens and snake eyes as being bad, lucky sevens as being good, but then someone was saying it doesn't really matter, right? Is that what you're saying? Yeah. It's just what you pick. So the movies are, I was totally had my trust in Hollywood that, because when you get a snake eyes in Hollywood, it's bad. You lose the whole thing.
Statistically the most likely, so the house wants 7 to be bad for you.
Yeah, exactly, because the probability against 7 is, as was just mentioned, is best. So it's so they made it up so that you'd go bet on 7 when it really is bad. Maybe that's a theory anyway. There's conspiracy theory there. So for instance, that is that probability. There's also the probability of getting a 3. Right? And there's some different ways to get that. You can get a 1 and a 2, or a 2 and a 1. Okay? And so forth and so forth. And I have these all mapped out in the notes. But a probability of getting a 7, of course, is your best bet. And there's a lot of different ways to get this. You can have a 1 and a 6, or a 6 and a 1, right? You can have a 2 and a 5, or a 5 and a 2. You can have a 3 and a 4, or a 4 and a 3. So there you go. There are your 6 possibilities. Okay? And you can just map out the whole scenario of getting different things. So x becomes this random variable, just what the sum is. And you can calculate the probability of any value of this random variable. So that's one example of a random variable. A second example would be basically, I want to toss a coin, okay, and with probability p it comes up heads. Okay, and what I want to do is define a random variable n, which represents the first time heads comes up. Okay, I'm going to keep tossing a coin until heads comes up. Okay. Then this random variable n, I can define the probability that n equals 1. If it comes up on the first time, I know it has a probability p of coming up heads, so that probability is p. Okay? If it comes up on the second time, then the first time I flipped it, it had to be tails. And it comes up tails with probability 1 minus p, and then it comes up heads p. That makes sense? And so forth and so on. And for instance, if you flip this coin n times, then on the nth time it comes up heads. That means n minus 1 times it came up tails. So you have 1 minus p, n minus 1 p. Okay, so something like this. Again, just another definition of a random variable. Okay? And then we can start calculating. So these are calculating probabilities of these defined random variables. Okay? All right. And by the way, these are all what are called discrete random variables because there are discrete outcomes. There are discrete values for the random variable. You can't say n is a half. There is no half toss, right? I mean, these are integer numbers, so you have a very well-defined discrete set of points on which your probabilities live. Okay? And we can define what is called a distribution function for any probability. More generically, now we go to the broader picture, which is a distribution function called f of b, is the probability that the random variable x is less than or equal to b. Okay? So you look at something like this distribution function accounts for all outcomes less than b. Okay? And some properties of f of b that we should note. So first of all, f of b is non-decreasing. As a function of b. Okay? So in other words, you keep adding events, and this is only going to get bigger, right? Your probability of hitting more and more events will be bigger and bigger. You don't go backwards. Okay? Probabilities are defined between 0 and 1. All right. The limit, as b goes to infinity, of f of b is equal to f infinity, which is 1. In other words, if you take into account all potential possibilities, then with probability 1, you will get one of those outcomes. B are the outcomes, right? So you think about B as being all these possible outcomes or all the possible outcomes, and you handle all possible outcomes. When you do something, if it's a head-tail flip, it's either heads or tails. Those are all possible outcomes. Well, with probability 1, you will get one of those two outcomes. If you have 10 outcomes, if you account for all 10 outcomes, then with probability 1, you're going to have one of those 10 outcomes. Okay, so that's that. And the limit, b goes to negative infinity. In other words, you don't account for any of the outcomes. The probability of not hitting any of the outcomes is 0. All right, so these are just intuitive concepts that we define. Every statistical question you would want to ask about a random variable or discrete form can be answered in terms of this distribution function. Okay? So for instance, the kind of things that you might want to ask is the following. What is the probability that your outcome is between sum A and B? That's the generic question you want to ask, right? So you have a bunch of outcomes, and I want to look at a specific subset of outcomes. And let's just say it's between A and B. Then this is something that would be defined as this. All outcomes less than B is f of B, and you subtract off of it all outcomes less than A. Okay? So it is. So once you give me that distribution function, you're set. Here's the thing about distribution functions. For very easy examples, you can come up with a distribution function. Part of the issue with this course is part of what I want to gear the course towards is you have some data. And you don't know where the randomness is coming from. You don't know what the distribution function is of the probability, right? This is part of the problem with a lot of problems, is that you don't have this. We're making up all these examples. We're very simple coin flips, die tosses. We can completely calculate what this f is. Generically, for hard problems, things you're going to face, you don't know what f is. And so we're going to have to talk about what that means for you. Okay? All right. So associated with this, too, that's the distribution function. There's a probability mass function. Which relates to the probability, which is called little p, which is p, that the variable takes on a specific value. Okay? P of A says, when does this discrete random variable take on the value of A? And since it's a discrete random variable, what we know about a probability mass function, it has the following type properties, which is it's either bigger than 0 for x being one of its events, or 0. For a discrete random variable, you give me a set of events, x1, x2, x3, x4, and then I can calculate some non-zero probabilities of those things happening. Otherwise, it's 0. So, for instance, this probability mass function for the coin flip that we just did, so of saying the sum of two coins, your events are here, x equals 2, the sum is 2, the sum is 3, the sum is 4, the sum is 5, all the way up to 12. That's your whole event space. And each one of those has some probability assigned to it. But anywhere in between, x equals 2.1 is 0. There is no probability that you can have 2.1 heads. Or, sorry, the sum of two dice is 2.1, right? Unless you're really bad at math. Okay. My daughter, she's 4, she could totally get 2.1 out from adding two dice together. That's how awesome she is. I don't want to discourage her creativity yet. All right. Everybody go with that? So all cases of discrete random variables, these are the kind of things you calculate. Other things to do with the probability mass function. Here's the definition. If you sum up over all events, you could have up to infinite number of events, depends upon how you define things. It's probability 1. Probability that you land on an event, of course, if you consider all events, is with probability 1. You're going to get one of the outcomes. Okay? All right. And finally, how do you relate this probability mass function back to the distribution function? So to relate this probability mass function, which really involves the probability of a specific event, back to the distribution function, which is all events less than a specific value, well, then you just have to sum up all the events below that, right? So if you want to relate this to the distribution function, you say something like this. Here it is. You sum up all the probabilities of all events less than A. Okay? And that's it. It's probably actually less than or equal to A. Right. By the way, again, I'll send out my notes, and part of your job is to read it and feel free to send me commentary. Say, by the way, I think that's supposed to be less than or equal versus less than. I think you misspelled your name. Whatever. I can take it. It'll help the notes out, so please feel free. So that's the relationship. Probability mass, and here's the distribution function. And these are the definitions. And this is all in the context of discrete random variables, where you have specified and discrete outcomes. Okay? So now we'll consider what are called continuous random variables. All right? Now, continuous random variables are variables who have essentially an uncountable number of outcomes. Okay? And so in this case, you think about it as being a continuum of outcomes. Okay? So there's an infinite number of outcomes that can possibly occur in a continuous variable. So what we define then is the following: the probability of x being in some, let's define some event or some set. So it's a set of outcomes essentially on some continuous random variable. Then the probability of being in that set is just given by an integral of f of x dx integrated over the set B. Okay? In this case, f of x is a probability density function. Okay? Just as you would expect. One thing you learned from very early on in calculus, second quarter calculus, second or third day in, you started talking about, hey, isn't an integral just really a sum of rectangles added together? Sums and integrals are about the same. Well, this is the same thing here. This is the continuous version of this discrete definition. That essentially, when you go to the continuum limit, becomes an integral. And your little p here, which is the probability mass function, is your density in that context. And this here is the integral of that, which is the probability here. Okay? So there you go. That is how we define these things. Couple properties. The probability of x, for instance, being in, if I integrate over all the domain, in other words, all possible outcomes, I have to get 1, right? If I look at events and I integrate over the whole event space, probability 1, I will be in that event space. Okay? All right, remember, how do you win an argument at the end? You tell them it's with probability 1, I'm right. All right. Has anybody tried it yet? No, yeah? Nobody? Try it with your wife or boyfriend or something. No, okay, boyfriend you might be able to win, or girlfriend, they might still give you that credit. A wife or a husband would just completely ignore you, or perhaps knee you or elbow you. Okay, I know better. See, I can make jokes in class, and then that's safe. All right, so there you go. I know I couldn't win an argument with that, but you still might. Maybe I can convince you to try it at least. All right, so there you go. You have that. You have everything defined there. And then the probability, just as before, of some event being between A and B. What do? You integrate between A and B. That is the probability that that variable takes on a value between A and B. A couple things to note that are quite different, by the way, between continuous and discrete. First, what if I say I want the probability that it takes on exactly the value A? Well, so the interpretation here is for continuous random variables, with probability 0, it takes on a specific value, right? It's a continuum of values. So in one way of thinking about it, if I have an infinite space of places, right, everybody has some probability of happening, so I cannot weight this specific event, unless it was a delta function type probability distribution, which we don't have, any more than any place else. So the specific event finding exactly some place is 0. Okay? Whereas in the discrete case, right, if that is an event, you have a finite probability. But all these probabilities have to add up to 1 when I integrate from negative infinity to infinity. Okay? Whereas in the discrete case, I just have to sum up all the probabilities, and it has to add up to 1. And so if I have an event that occurs for this value, I can just add it in there. All right. So this is the idea of the density, and then we can also define the distribution function here too, just like we did in the continuous case. Or sorry, just like we did in the discrete case. This is essentially the integral of this thing, which is the probability that x for all A from negative infinity to A, everything less than A, is just simply integrate from negative infinity to A, this distribution function dx. Okay? Ultimately, the real interpretation, yes?
Not call that a cumulative distribution?
Yeah, so you can call it a cumulative distribution. Oftentimes, it depends on, by the way, what you will notice, right? Go and look like, hey, I would like a statistics book to look up some stuff. You get some, and then all of a sudden you go to the UW library and you type up, okay, let's look at some statistics books. And you get how many? Probably like 1 billion. Okay, and some books call it cumulative distribution. Some say, hey, you can call it cumulative distribution or just distribution. They drop it. Either way. Cumulative is really hard to spell. Like you sometimes forget, is it 2 M's? Is it 1? It's, you know, I have a rule about spelling in class. I try to avoid doing it if I can. All right? So there you go. That's the definition. Distribution is not bad, but I'm going to start, just calling it dis. All right? Because then I'll spell the whole thing out. All right. So how do we interpret, by the way, this f of x, this probability density? In many ways, a lot of us already have sort of an intuitive concept. But let me ask the following question. What is the probability that the random variable is between a minus epsilon over 2 and a plus epsilon over 2? Where I take epsilon to be small, right? So then this is simple because you integrate between a minus epsilon over 2, a plus epsilon over 2, f of x dx. And if this epsilon is small, you can approximate this integral by epsilon fa. So essentially, the f gives you the weighting of the probability. What f does is it tells you the weight of the probability for the value a. Okay? But if you tell it exactly a, it's 0. All right? But it still carries the information. It's tells you the likelihood it's going to be in some place there. All right. So those are some basic concepts for continuous and discrete variables. And in different contexts, you'll be working with either one. The ideas between the two are basically analogous. You just replace integrals with sums, things like that. Okay. But now I want to illustrate to you some of the more famous of the distribution functions or probability density functions. We'll start off with the discrete case. There's the Bernoulli variable. Okay, the Bernoulli random variable, basically, if you consider a trial and outcome, and the two outcomes are success or failure, so like an indicator function, essentially. That's the importance of it. So we'll let x equal 1 be a success, x equals 0 be a failure. Clearly not a PC term. We would call this, you know, not quite a success in today's language. Okay. You know, we don't have to be so negative. So those are the two outcomes, and we can say, okay, suppose we have the success rate, or probability of getting a 0. Let's call that, and the probability of getting a success, we'll call that P. There you go. It's a very simple, it actually goes right back to our coin toss example we did at the beginning. So this is a very important function, you know, because a lot of examples, you just say, did I get a success or a failure? There's some probability of success, some probability of failure, and the Bernoulli variable is really incorporated into the next one we'll talk about, which is the binomial random variable. Because this is an individual trial. In the binomial random variable, you consider n trials with some p for a success. So as you take this Bernoulli example, and now you say I do n trials, and I ask the following question. I want the probability, x, of getting n number of successes. Okay? In that case, so what I can calculate is the Bernoulli random variable, j, is given by here. These are the number of successes, j. I have probability 1 minus p of a failure there. Now, since I have n of them, I have this binomial coefficient out front. And the binomial coefficient is defined as n factorial over n minus j factorial, j factorial. And what this tells me, it's basically the way that statisticians talk about a probability theory. You say, this is n choose j. Okay? I have n total trials, and there's j ways to get a success. Sorry. And I have j successes in those n trials. And then this is the number of ways I can get those j successes. Okay? So consider, for example, I have 3 trials, 2 successes. Then you can calculate this thing, and you can calculate this to be 3 is equal to just 3. Well, what are the 3 different ways I can get 2 successes and 1 failure, essentially, in 3 trials? Well, you could have a failure, success, success. You could have a success, failure, success. You could have a success, success, failure. Right? So this is just different ways you can count that in your trials. So this becomes an important thing. You see it all the time. Binomial variables are like one of the most common because they deal with the most simple thing imaginable, successes and failures. You are all successes, by the way. Let me just throw that out so you can feel good about yourself at 9 o'clock in the morning. We're at 9. Okay. Poisson. Here is the definition. This is kind of a really famous variable because a lot of people do Markov process, Poisson processes. They basically talk about exponential waiting times between events, and this is the variable that sort of models that, where lambda is some parameter which is greater than 0, which becomes your the important variable of telling you about the exponential waiting time between events, for instance. I'm not going to go into too much detail. just write it down. There it is. These three are probably the most famous that you see over and over and over and over again. Okay? So that is the discrete case for random variables, the most common that you'll see. Now we go to continuous. And in the continuous, you have the uniform random variable. The uniform variable is just you define basically your probability density function as being 0 or so you just define it over some interval. It's equally distributed on an interval. This is some amplitude, some constant. The area under the curve is 1 because it has to be. That's it. So you just uniformly distribute over some interval that's given to you. Here it's alpha and beta. By the way, associated with the density is the cumulative distribution, which is, if you integrate that up, just there it is. Alpha, A, beta, and A is beta. So you just integrate that thing up, and you get your cumulative distribution. There's an exponential random variable, which is essentially the equivalent of the Poisson for the continuous case. And I'll write down the granddaddy of them all, the normal distribution. There it is. Gaussian. The idea is that you have basically the way this is constructed. Mu, which we haven't talked about yet, is going to be our mean, and sigma will be our variance. We'll talk about mean and variance next. Okay? This one here is probably the most important one because we're going to talk on Friday about central limit theorem, which, if you have a large enough sample for any continuous variable, if you go to an infinite number of trials, everything, no matter, regardless of what kind of distribution it has, it goes to the normal distribution. And by the way, this is one of the assumptions that everybody makes in modeling data. It's like, well, let's assume I just have enough data to call it normal, because there are all these really nice tests for normal distributions. Your data might not be a normal distribution. Okay? So anyway, there's something to keep in mind. It's very nice to work with. If you integrate it, you get the error function. And that's probably the most popular lookup table math formula in the world, right? Does everybody use the error function lookup? Right? I think no? In the back of a book, error functions, you look them up? Okay, so anyway, I don't look up my things in a book, but that's the one I've looked up a lot of things on. All right. Probably look it up on Google now, I'm sure. Okay. So that gives us these two. There's one more in here that's exponential I show you. And now what do we want to do with these things? Well, notice a couple things that we're starting with. We're starting with the idea that we actually know our distribution functions. Okay? Ultimately, what we're going to do is to say, well, we really don't know them. We're trying to actually maybe guess what they might be. Guess some of the parameters of our distribution function. For instance, that distribution function for normal, there's this parameter sigma and mu. I'm going to have to take my statistics and try to pull out what those things are. It's parameter estimation ideas, okay? So, but how do you talk about the expectation value of a variable, the variance of a value of a random variable? The expectation is just simply defined as so, which is for a discrete variable for all the x, with p of x being positive. So you basically sum up over all your sample space, and that is your expectation value for that variable. Same thing for the continuous. Except it's an integral. Essentially, what this is a mean, what it's commonly called. And by the way, depending upon your scientific home, you'll see different symbols for the expectation. For instance, oftentimes people do that. That's pretty common, x bar. If you're from the physics world, you might start doing some of that, some Bernoulli and Kutz around that thing. Same thing, right? So quantum mechanics, this is the standard way you write everything. In Bernoulli and Kutz notation, expectation values are everything there. Okay? Because essentially the way quantum mechanics is formulated is the Schrodinger equation is a probability density function. Okay? All right. Not much more to say there except that you can calculate some expectation values for these. I give them in the notes. I'm not going to write them down. But basically, I calculate for these continuous and discrete examples that I've given you here on the board for the binomial, the Bernoulli, the normal distribution. I give you out what these how do you calculate these averages or the means, what they come out to be, the first expectation. More generally, by the way, you can compute. Suppose you're not really interested in the average value of some random variable x. You're interested in some function of x. Okay? In other words, x itself is not your priority. You want to know something else about x, and you want to actually understand what is going on with something like this. And you might ask some probability questions about some function of x, and you say, well, I want to know what the expectation of that is. Well, you just use these same definitions, and it's basically, in the discrete case, it comes out to be this, and in the continuous case, there you go. Okay, so you generalize this idea of looking for a function or expectation of a function of this thing. All right? The thing that most people do is look for what are called moments of this thing. In other words, when g of x is something like this. So, when n is 1, it's just the straight up expectation. When x is 2, it's a second moment. X is 3, it's a third moment. X is 4 is the fourth moment. The third and the fourth moment have names like skewness and kurtosis. We're not going to talk much about them. They're just names that basically the third moment tells you how skewed the distribution is. In other words, is it looking like that? You'd have a nice skewness. Kurtosis tells you if it looks like that versus like that. But who cares for right now? Those are just variables. The most important of them all is the second moment. And typically, we mostly concern ourselves with the first and second moments of random variables. Because in the second moment, we define the variance. Okay? So that's a concept that a lot of us have, at least intuitively in our head. And the way you define the variance is as follows. The variance of x is equal to the expectation value of x minus expectation of x squared. So that's the definition of the variance. And if you do out this calculation, which is not so hard to do, this can actually be written in a more convenient form as the expectation value of the second moment minus the expectation value of the first moment squared, or the mean squared. Okay? This tells us something about, I have some mean, and the variance tells us about how wide that thing is. We really care, actually, about how wide this thing is. It tells us how our probability distribution is sort of spaced out in our probability space. Okay? Generally, I think that's probably what most people are familiar with. You calculate means and variances all the time. Standard deviation is just the square root of the variance. Okay? So this is something we always hear about as well, standard deviation off a bell curve, and you say, how many standard deviations am I away from? How many standard deviations above the curve am I? That's the kind of question we like to ask. We never ask about how many below. Like, okay, so we like to always believe we're way in that tail. Not on, but the good tail. There's a bad tail and a good tail. Okay. All right. But you know, here's the thing. If you look like this, a good tail, if you just look the other way, you know, you just have to stand on the other side. If you're on the bad side of the tail, just go around it, and then it looks like you're on the good side again. I'm just trying to help you out with positive thinking. Is it working? Not yet? Okay. Maybe in time. All right. Any questions on this so far? Standard stuff, standard definitions. A lot of it's definitional. Again, what we're going to be using throughout the quarter. All right, so that gets us everywhere, all the stuff we need to put in place before we talk about the most important part of what we want to do, which is when we start talking about data analysis, what we're interested in is we have a bunch of random data, we're measuring different things, and what we're really interested in is looking at, hey, does this data, is it correlated together, for instance? How are they related? That's one thing that you always ask about in data analysis. You want to know, do the variables play a role with each other? Okay? So to start addressing that issue, you have to start talking about joint probabilities and joint distributions of variables. So for instance, I can define, and let's just do it for the continuous case, the probability that x is in A and y is in B. So let's consider two random variables, x and y. And what I'm asking about is essentially their joint distribution. Okay? I'm looking to find the two variables here, and what that basically turns out to be, you just generalize your definition. You integrate over the space, and now you have a joint density, f of xy. And that's the formal definition of that thing. Okay? You can also define moments just as before. The moment of some function of g of x and y, or expectation of some function of x and y, one second, which is equal to, integrate everybody from negative infinity to infinity, put this g of xy in there, times your f of xy, dx, dy. Yeah? Oh, yeah. I didn't even pay attention. So, yeah, you should, the dy goes with, yeah. So I have the dx out here, the dy there. Yeah. Here, I can't even mess up because I got a negative infinity. They're both negative infinity, so, okay. Everybody good with that? So there you go. All the same concepts follow through, just that now you do double integrals on everything. Two key ideas come up from this. One, the idea of independence. I have two random variables. Maybe I take the following random variables. The temperature in the room as a function of time versus everybody's shoe size as a function of time. And I'd say, are they correlated? For instance, I could ask, are those somehow dependent upon each other? All right, so you can ask that question. I mean, it's a little bit made up, right? No? I mean, I'm sure Nordstrom's was thinking about it. Okay, we got to get the right shoe for the temperature. No? Nobody's thinking that? All right. Here's the, by the way, real tip. I bought a pair of shoes in Minnesota once in the middle of winter in December. Do you know how cold Minnesota gets in December? Like anyway, super cold. You're walking across the parking lot, and you know how small your feet are when you get inside? Well, it turns out that's a bad time to buy a pair of shoes because your feet shrunk. All the blood was rushing to your head just to keep you alive. Okay, and your feet have no blood in them. And then you try on a pair of shoes. Hey, this fits great. And then you go home later, it's warmed up. Or you get to the wedding where you're supposed to be wearing these shoes, and you go, geez, these are like 10 sizes too small. Write that down in the notes. Okay. All right, so independence. And what independence says is if I have, essentially what independence is going to result in is the following statement. If I ask about the expectation of a separated variable like this, then this becomes, I can actually separate it out as the expectation of E times the expectation of h of y. Okay? That is the definition of two variables are independent if that's true. Okay? If that is not true, then they're dependent. And the degree of dependency is something you're very interested in. This is ultimately what we're very interested in this class. What is the degree of dependency on different variables that we're measuring? We do not know oftentimes what the distributions are, but what we want to do is empirically formulate the following. I have some variables that I'm calculating or I'm taking in, temperatures, barometric pressure, whatever kind of things you might take, and you say, are these guys statistically related to each other? And the way, sort of the most common way to make that assessment is by calculating what's called the covariance. Okay? The covariance between two random variables, x and y, is equal to the expectation of x minus expectation of x, y minus expectation of y. Notice that the definition looks a lot like the definition of variance. Except, if this was xx, this would just be the variance. Okay? The covariance of two variables is the same. It's just the variance of that variable. And then you can do a little math to work this out to find that this is equal to the expectation of x times y minus the expectation of x, expectation of y. You can calculate these things. Now here's the thing to notice. If it's independent, what is this? EXY becomes EX times EY, which is the same as this. EX times EY minus EX times EY is 0. So if the covariance is 0, then that means they're independent. Otherwise, you calculate this quantity. So these are all definitions. And now we go to how MATLAB is going to help us calculate these things. Yeah?
So the two events are independent if that thing is true for all G and H.
That's right. Okay, so MATLAB. So we're getting set to be close to programming. A couple things in MATLAB you might want to know about. RAND, MN, random number generator. It creates a uniform distribution between 0 and 1, okay? And it fills in a matrix of size m by n. Then there's RAND N, m by n. Creates an m by n matrix where every component of that matrix is normally distributed with mean 0, variance 1. And by the way, from that random distribution of mean 0, variance 1, you can formulate it to any variance and any mean you want. Okay, just a simple change. Mean x. You give me a matrix, and mean x calculates the mean value, or the first moment, of every column. It gives you back a row vector where every component is that. Okay? Same thing here, var x. For every column of this matrix, calculates the variance. STD x. Sounds bad, huh? Use this command sparingly. Latex gloves on your hands. Standard deviation of every column. Okay? Here's the best one of all. Covariance x. Now, if x is a vector, it calculates the standard deviation of that vector. If x is a matrix, and the idea is for these matrix, each row of the matrix is an observation, and each column is a variable. Okay? So I do a bunch of observations, those are the rows, and I calculate some variables. Temperature, pressure, blah, 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 blah. And I ask the following question, how are they related? That's what the covariance tells me. And what this does is it creates the covariance matrix. And along the diagonal of that matrix, it tells you how one variable is related to itself. In other words, it calculates the variance. So the diagonal of that matrix is the variance. The off-diagonal elements tells you how one variable is related to another. It gives you the covariance factor between those. Covariance of 0 is independence. Covariance of 1 is complete dependence, as it were. Okay? So you have to just see, it's like, what's my covariance values? And that tells you the strength of the correlation between two random variables. So all this stuff is sitting there, and a lot of stuff we're going to do is build codes based upon these simple ideas. All right, more Friday. Have a nice Wednesday. And notes will go up soon, in like 10 minutes.